All right, let's take a look at an example that uses tables and the rectangular approximation method to get us an answer that is useful. This one's not about velocity and time. This is a different setting. So this is about cardiac output. You can do some of the reading up there. For this, what we need to know is that we're trying to measure the cardiac output, how much blood is flowing through the heart in any given second, and give some standard measurements up there. One way to do this is to inject the patient with some dye, and then every few seconds you measure the concentration of the dye as it comes out of the heart. This is a graph and a table that measure some of that. So we've got the time here, 5 seconds after it was injected, and the concentration. The concentration is in milligrams per liter. This kind of shows a graph there. And so if we want the cardiac output, okay, when we look at this graph, because it's the data that we have, if we were to do areas of rectangles here, however we decide to make those rectangles, the area of this rectangle, because this is milligrams per liter tall and seconds wide, it will have units of milligrams per liter times seconds. Now our cardiac output, what we want to know is how many liters per second. So we have some of the right units that are in there. We just need to manipulate those in the correct way. So for one thing, if we took this and we flipped that over, so if we looked at 1 over milligrams per liter times seconds, we would get liters per second times milligrams in the denominator as well. Okay? And that's close to what we want. We just have this extra bit of milligrams in there. But if we know how much dye was injected in the first place, so if we multiplied by the amount of dye injected, which would be in milligrams, then we could get these milligrams units to cancel, and we'd be left with liters per second. So we can figure out how to manipulate the units that we have to get the answer that we want. Okay, this concentration in our graph started at 0 and it ends at 0, so the blood would have processed all of the dye at that point. Okay, it goes through the system pretty quickly. And so if we figure out an approximation of what the area under this curve that looks maybe something like this, if we can figure out what this area is in here, then we can, and we know that we injected 5.6 milligrams of dye in the first place, then the 5.6 divided by this answer that we get there should give us the cardiac output. Okay, so a little bit there about how important it is to look at the units that you have, and how if you manipulate the units that you have, you can sometimes change them into something that you actually want, and the processes, the mathematical processes you have to go through to make the units right very often will make the problem right. I've made a living in my physics class by making the units work out. Okay? So the one rectangular approximation method that's not going to do us any good here is the MRAM. We don't have midpoints. Okay, so we could go through and we could do an LRAM though. We can see that the gaps here are always 2. So that's the width of every rectangle. Width of every rectangle is 2. And so I could figure out the areas of these different rectangles. This, as we did it before, this would give me a 0, This one, 3.8 times 2 is 7.6. This is 16, 12.2, 7.2, 4.6, 2.9, a 1.82, I think, yep. A 1.14, a 0.72, 0.46, 0.28, 0.18, and a 0. And so my LRAM, if I want my left-hand sides, then I'm never going to use the last one, and I'm going to add up these. Okay. Now we're going to see something interesting in this one, because if I want the RAM, then that is never going to use the first point, so this one is not going to get used by the RRAM, and so it's going to use all of these. But of course, if I look at it carefully, it's just all those, the same numbers together. They're both going to estimate this to be exactly the same thing. Okay, so it just becomes a matter of adding those numbers together. 7.6 plus 16 plus 12.2 plus 7.2. We'll try to do this relatively quickly without making any stupid mistake button pushes. That's 1.82 plus 1.14. I'm on my calculator right now, by the way. Plus 0.72 plus 0.46 plus 0.28 plus 0.18. And when I add those all together, I get a 55.1. Okay. And remember, that is the units on that. That is milligrams per liter times seconds. Okay, so 55.1 milligrams per liter times seconds. And if I take my 5.6 milligrams that was injected in the first place, and I divide by my 55.1 milligrams per liter, I think that's what we said that we were going to do, we get 5.6 divided by 55.1 is, I get a 0.10163. And the units on this, this is times seconds, so this is going to be in liters per second. They actually prefer this apparently in liters per minute. So if I multiply that by 60, I get 6.0, about 6.10 liters per minute. In our initial data, it said for a person at rest, it might be 5 or 6 liters per minute. And so this looks like there's nothing in particular wrong with this person. So what you should have gotten from this is that it's not just about velocity and time. There can be other examples that work and are important here, plus that you can use a table, writing a program to do the table for you on the calculator. That's a little bit trickier business, but certainly putting this into the spreadsheet would be nice and easy for that. So that's the last little bit of information you need to be successful on the WAMAP assignment. So I will be opening that up for you.